Now that we know why a carrier is useful, we can ask how the message is placed on that carrier. In amplitude modulation, the message controls the carrier amplitude. When the message grows, the carrier envelope expands. When the message falls, that envelope contracts. In conventional AM, a strong carrier remains present all the time, so the envelope is easy to observe. In double-sideband suppressed carrier, or DSB-SC, the sidebands still exist, but the carrier itself is removed. So both waveforms are closely related, yet one keeps the carrier for simplicity, while the other suppresses it for better power efficiency. The frequency domain makes that relationship clearer. A single-tone message creates two sidebands located at the carrier frequency plus and minus the message frequency. Conventional AM contains those two sidebands and also the carrier spike at the center. DSB-SC keeps the same mirrored sidebands but removes that center carrier. So the occupied bandwidth is still twice the message bandwidth in both cases. Suppressing the carrier does not save bandwidth. It mainly saves transmitter power because the carrier no longer burns energy without carrying new information. For conventional AM, the modulation index tells us how strongly the message changes the envelope. If the modulation index is below 1, the envelope stays clean and easy to follow. At exactly 1, we are using the full envelope range without yet causing distortion. But if the modulation index rises above 1, the envelope folds over itself. That condition is called over-modulation. At that point, a simple envelope detector can no longer track the message correctly because the apparent shape of the envelope is no longer a faithful copy of the original signal. So, for basic AM reception, keeping the modulation index at or below 1 is a practical design rule. This is why conventional AM became so attractive in early radio. If a carrier is transmitted and the envelope is well behaved, a very simple diode and RC filter can recover the message. The receiver only needs to trace the envelope. DSB-SC is different. Because the transmitted carrier is missing, the receiver must recreate a synchronized carrier locally before detection. That usually means coherent or synchronous detection. So DSB-SC is more power efficient at the transmitter, but it asks more from the receiver. This is the classic trade-off between efficiency and implementation simplicity. Let us summarize the engineering picture. Both conventional AM and DSB-SC place information into two sidebands around a carrier frequency. Conventional AM keeps the carrier, which makes envelope detection simple, but wastes transmitter power. DSB-SC suppresses that carrier, which improves power efficiency, but requires coherent detection at the receiver. Neither method removes the duplicated sideband structure, so the bandwidth cost is still there. That naturally leads to the next question. If one sideband already mirrors the other, can we remove one and transmit only what we truly need? That is exactly where single sideband and vestigial sideband modulation enter the story.